I probably mentioned before that if you asked me what is physics, that I'd go on and on and on and on and on and on. There are lots of different ways to define it, lots of angles to go at it, lots of different ways of looking at it. So I had to pick one right here for the beginning, the very first discussion of the whole thing. So I decide this. But physics is a description of the universe. Immediately, I think of a whole bunch of caveats to that. But I'm going to leave it how it is. Why do I like it? Physics is a description of the universe. Because what I'm trying to do, or the reason why physics exists, because I look at my universe and I find that it's mysterious. I would like to understand the workings of the universe. I want to describe it. Now, when I first begin this task as an ancient scientist, not that I'm old, I'm saying if I lived way back in the day, before all of the great discoveries that have been made in the history of mankind have been made, perhaps I go out into the evening, I look up into the sky and I see the stars, the majesty of the heavens, and among the stars I recognize individual points of light that wander, and I call them planets. And I observe their motions day after day. I recognize their patterns. And I begin to formulate a more sophisticated description of my universe based on things that I can see and taste and smell and touch. It's not terribly long, based on the limitation of human senses, that I come to the end of the things that I can simply look at and describe. I'm going to do something more sophisticated. My observation of the universe ultimately comes down, and this is a very surprising thing. It ultimately comes down to taking observations of the universe that I can convert into numbers. It's a very simple, sophisticated, lovely idea. Simple and sophisticated simultaneously. It's a strange thing. When I observe the universe, I ultimately discover that nature is not random. Nature is not accidental. That nature organizes itself into patterns. Some of the patterns of nature are extraordinarily obvious. For example, if I hold my glasses up here and I let go of them, they fall to the table. That motion, that behavior of the universe, everybody in the room knows, without having taken a course in physics, that is gravity. That is an aspect of the universe. And when I investigate that aspect in a precise way, it becomes mathematical. The universal law of gravitation that you'll learn in this class is expressed as a mathematical equation. And some folks don't like that, casual observers of the sciences. That physics, it's not for me. It's all math. Well, physics isn't all math, first of all. It simply isn't. But it's not math because we think math is groovy, because we thought it might be fun to deliberately find a reason to use math. Physics is mathematical because the nature of the universe is mathematical and nobody understands why. There are questions that don't have answers, and one of them is, why is the universe mathematical? I don't know. Nobody really has an answer to that. We could discuss it. I've spent a lot of time pondering it. Maybe you could come up with a good answer. But here's one thing that I know. If I want to describe my universe precisely, then my eyes, my nose, my sense of touch, my hearing, not good enough. In order to examine the universe more closely, human beings have done a remarkable thing. We've invented ways of measuring the universe. I created a device, it's a construct of mankind, a device that I can hold up against the nature of the universe and convert my observation into a number. Well, now we're off to the races, and sometimes I think that that's where the math of the universe comes from. Because as soon as I have numbers, I think the math is created. Because as soon as I have one of these and one of these, well then I have two, and that is addition. And if I do that process again, now I have four, and that is multiplication. So as soon as counting happens, as soon as the nature of the universe is expressed as a number, math comes into play. And so here I am. I have this device that I will place up against the universe, and it will allow me to convert my observation of a phenomenon into a number. And then I look for relationships and patterns in the numbers. And the relationships among numbers and the patterns in numbers, they get expressed as equations. And equations can be transformed into other equations. And then there's algebra. And then there's trigonometry. And then there's calculus and differential geometry and differential equations and all of the different forms of mathematics devised by man to manipulate what comes from a measurement. So I measure my universe. And a thing that I'm very interested in is that my measurements of the universe are limited by the quality of the measuring instrument that I use. This ruler that I hold in my hand has tick marks on it. Tick marks down to the thousandth of a meter. That is, it has millimeter tick marks on it. So when I want to observe a phenomenon of the universe and I lay my ruler down, and someone has trained me to use it in the most thoughtful and effective way possible, and I look at it, there's a limit to its ability to observe the universe, just as there is a limit to the ability of my eye to precisely observe the universe. My eye is least precise. The ruler is more precise, but it is not infinitely. That means that I cannot know my universe at all to infinite precision. Here's a deep idea. There are two universes. There is the real universe, the natural reality of our cosmos, and there is the observable universe. There's the universe that I, as a human being, can measure, and they are not the same because my measurements are limited. You say, well, Scheidly, you have to try harder. But here's the thing we've discovered, quite recently, in fact, we've discovered that there is an actual natural limit built into the universe for our capacity to measure. And so it's really quite astounding. So where my description of the universe begins is with measurement. And so the first unit of our physics is going to be all about how we do measurements for real. And you might be surprised that true scientific measurement done properly is almost never taught. And when it's taught, it's seldom learned. And when it's seldom learned, it's seldom appreciated. So what I'm going to try to do over this next unit is give you an appreciation of why what I'm saying matters. It's going to be difficult to do because in my description so far, I've said math and numbers and counting and measurement and things. So it's going to be a little bit of a rough ride. It's going to require intellect, a little bit of creative thinking. And it's going to require some fundamental skills, and I'd like to describe those skills. The first involves something that you're already aware of, I think, and that is significant figures. Some of us may already have been trained regarding, I guess you would say, the rules of significant figures. And it wasn't fun. I know it wasn't fun for me. It's particularly difficult if you fail to appreciate why there should be such a thing. And so what I'd like to do is to describe to you. You might imagine, oh, I know what's happening. There's a list of rules coming that says that zeros after the decimal point are significant, but non-zero digits are significant, but zeros before the, after the, whatever. Like there's some sort of list of rules. I'm not a fan of the list of rules. I'm going to show you the list of rules. I actually have it in the presentation, but I'm not a fan. What I'd rather do is understand why it should be so, because if I understand why it should be so, then it won't be difficult for me to determine the number of significant digits. A thing happens in math, and I verified earlier today that it's still happening, that in math class, when I do calculations, apparently I round to tenths. So we're trained to do in math class is round your answer to tenths. Why? Well, there's no better reason than math teachers don't want a bunch of digits written down on a piece of paper. They'd rather just see the smallest compact answer. It's easier to grade. There's no mathematical reason why one number that is very precise, that is, has lots of digits after the decimal point, is better or different or special in any way from a number that has lesser precision, that is, fewer decimal points. So since that's the case and it doesn't matter at all, you might as well just use numbers to tenths. Just let it be that. Correct answers, incorrect answers. But in science, I can't do that because every number that I encounter in science is the result of a measurement. Every single thing I know about the universe is critically important. It's critically important. It's subtle, but it's important. Every single thing that I know about the universe comes from putting a device up against the universe and converting that observation into a number. Everything. So every number that I work with in science is the result of a measurement. And this measuring device, like every measuring device in existence, it doesn't matter how fancy it is. It doesn't matter if it's some university scientific lab with lots of pipes and wires and fancy scientific apparatus. It doesn't matter if you use computers. It doesn't matter if you use laser beams or some other nonsense. Every measurement has a precision. Now, the precision of this ruler is to the millimeter. That is, this ruler can measure to the 1,000th of a meter. So if I write that down, 1,000th of a meter, a tick mark in my ruler represents 0.001. because that is the thousandths place. That is the precision of my ruler. I cannot measure better than that. Maybe I get a different measuring instrument. If I really need to know, I might get a better one than this. But there's always a limit, always. So if I made a measurement like this, I'm making up numbers, 6.238. Those numbers are all significant, because I made the measurement with a measuring instrument that is precise to the 1,000th of a meter. So that 8 there, that matters, because I counted out 8 actual tick marks, real tick marks. That makes that 8 significant. And because it's the most precise digit, every digit in front of it is significant as well. Every digit in front of it is significant as well. But maybe I use the same measuring instrument one day and I come back and I say it's 2, 3, 0.59187. Oh, now something's happened. You would be suspicious of that. Because I have a number in the thousandths place, but I have numbers beyond. And you would say, where did the 8 and the 7 come from? Oh, well, I thought that'd be nice to have an 8 and a 7 on the end of my measurement. You say, no, I know that ruler in your hand can only go to a thousandth of a meter. These numbers are not significant because they are beyond precision. So you see, the idea of significant figures and the idea of precision of a measuring instrument are intimately associated with each other. Now, I'm going to assume for the rest of the discussion that we're all honest, that we would never lie about a measurement. We'd never make up numbers, because that's just dishonest. We never lie. We'll make our measurement honestly, and so we'll report it with thousands. So, if someone comes to me one day, and they tell me that they made a measurement 23.21 centimeters, that's 4 significant digits. And I know, by the way, that they used a measuring instrument that measured to the thousandth of a centimeter, because the precision of that number goes to the thousandth of a centimeter. And that's really easy. And so you make a rule in your head according to that. I get it. All those digits are non-zero, so they're all significant. No problem. Yeah, it's true in general. It's true that any digits that are not zero are significant. And it's got 4 digits, and so there's 4 significant digits. That's the weight of that number, 4 significant digits. But what about a number like this? You see, there are the zeros there, and 6 and a 2. What do I do with that? Oh, no, wait, there's a rule. I don't need a rule. Because when I do science, and I've experienced this before, because in chemistry I came across Avogadro's number, 6.02 times 10 to the 23rd things in a mole. Don't worry, by the way, no moles in physics class. Enjoy that thought right there. There's not going to be any mole. But 6.02 times 10 to the 23rd things is a mole of thing. But it's a very, very large number, so you write it in scientific notation. Writing numbers in scientific notation is an important skill. If I take 0.062 and I write it in scientific notation, it is 6.2 times 10 to the 2 minus 2. I use a power of 10 to represent the bigness or the smallness of numbers. A number that has a positive power of 10 is generally going to be a large number compared to the base unit. A power with a negative exponent is going to be a small number with compared to the base unit. Right? We understand how that works. But the bit that you might not have considered is that when you write a number in scientific notation, both of the lead digits are significant. Every digit in a scientific notation number is significant. The answer is 2 significant digits. The reason why the 0 and the 0 don't count is because they don't give me any information about the measurement in terms of the value of the measurement. They just tell me about the bigness or the smallness of the measurement. So I don't learn anything from that. So that has 2 significant figures. This, now, here's the thing. Here's the trick. It's the same number again, but now I have another digit on the end. That is, this measurement is more precise. It was made with a better measuring instrument. It was made with a better measuring instrument that has tick marks all the way down to the tens, hundreds, thousands, 10,000ths place. It has tick marks to there. That 0 means it came to that 0th tick mark. The measurement includes that 0. That 0 is a real thing to the precision of the measurement, so it's significant. That 0 is significant because it's part of the measurement. It's meaningful information. That's why it's significant, because significant digits describe measurements. 5,000, 0.5007, 4 significant digits. If I write them in scientific notation, I can't eliminate the middle zeros. Those middle zeros aren't just keeping a place. They're read off the instrument. And if the number is read off the instrument, then that number is 4 significant digits. Here's a funny little bit of business. 80 centimeters is ambiguous. Is it 2 significant digits or is it 1 significant digit? I can't tell without asking the person who made the measurement. So there's a kind of reality here. You can't just look at a number and know. You have to know what happened when the scientist went to the universe and made the observation. It's a thing that actually happened. It's an interaction between a human being, the universe at large. So I ask you, what happened? When you measured 80 centimeters, did you take a rod that was 10 centimeters long and flip it over 8 times, end over end? Then the answer would be 8 rods, 1 significant digit. The 0's not significant because if I have a 10 centimeter rod, I don't get fractions of a 10 centimeter interval. I get 8 10 centimeters, 1 significant digit. Or when you tell me that it's 80 centimeters, did you do a funny thing and take a 1 centimeter ruler and flip it over 80 times? That would be 2, wouldn't it? Because that 0 would mean something. That 0 would mean you didn't flip it 81. You didn't flip it 79. You flipped it 80. The 0 matters. It's 2 significant digits. The funny truth about this, 80 centimeters, the reason why it's ambiguous is that we have certain numbers, we have certain habits with math. One of our habits is that in order to write 80 with 2 significant digits, I must put a decimal point after it, and we never do that. The only time you're ever going to put a decimal point after a number and not have another digit is if you write a sentence that says, my grandmother is 80, period. Never do we put that decimal point. But if the decimal point is there, it means 2 significant digits. If the decimal point is not there, I don't know. It's ambiguous. But if it's not there, I think it might be 1. But I've got some questions. It's important to have questions because it's science. I can ask all the questions that I like. This is not the only time we do this, silly, silly humans, by the way. How often do you put a plus sign in front of a positive number? Sometimes you do, but almost never. Numbers without a sign are assumed positive. Negative numbers get a negative in front to let you know that it's negative. It makes it seem like negative numbers are different than positive numbers, and they're not. They're all real numbers. They're just on different ends of the number line. They're just on other ends of the number line. Now, here I have 80.0, and again, this is indicating an increase in precision. That's why it has 3 significant digits. Being able to identify the number of significant digits in a number is a skill that I expect you to have. I'm going to give you a greater skill shortly, a skill that very few people actually have. It's more powerful. I'm going to give you a greater skill shortly, and it's going to require that you have this skill, identifying the number of significant digits in a number. Here is the first reason why it's important. When I make this measurement of the universe and that measurement of the universe, that's fine. I'll take those measurements, write them down somewhere, but at some point, I'm going to be looking for patterns in the measurement. That is the nature. That's my physics, finding the description. And when I look for patterns, chances are I'm going to do arithmetic with numbers. And for that, I need a calculator. We say, oh, Scheidly, I got a great calculator. I got this TI 5000 nitrogen-cooled supercomputer pocket help thing. This is my calculator. This is the calculator of a physicist. It's solar. Don't need batteries. Now people have calculators and like, Scheidly, do you have a charging cable for the calculator? Charging cable? Mine charges on the sun. I had a funny high school physics teacher, a real weirdo. I could tell you stories. But he asked the question and confused everyone by saying, if everybody turned on their solar calculators at once, would the sun go dim? No. But my calculator never needs batteries. You might think that a physicist would have a super fancy calculator, and that's not the case. I have this calculator because I use my calculator to do arithmetic. I use my brain to do math. Do not rely on this too much. I do have one for special occasions, fancier one, also solar. By the way, this one, $5. This one, the super fancy one, $12. It's practically disposable and solar powered, but this one's got the trigonometry on it. Sometimes I get lazy and I like to have a button that just gives me the trigonometry. But I'm going to use a calculator. My calculator doesn't know anything about the universe. My calculator doesn't know anything about science. My calculator certainly doesn't know anything about significant figures. And I'll prove it to you. Here's this number, 2.0. How many significant figures? 2. That 0 is significant because that is reporting to me a measurement from a device that had tenths. And if that device had tenths, if that's the precision, then that 0 is significant. 2 significant digits. 2 significant digits. So I'm doing a division with numbers that have 2 significant digits. When I do that, my calculator says 0.66666666666. Infinite significant figures. The number has become infinitely precise, infinitely significant. That can't happen, can it? I can't take some mystery and uncertainty and put it together and get certainty. That can't be. It turns out, and you know this, because you know there's an expression, that a chain is only as strong as its weakest link. Well, a calculation is only as strong as its weakest number. So look for the weakest number. I've got a number that has 2 significant digits and a number that has 2 significant digits, so they're both sort of equally weak. My answer can only be good to 2 significant digits, and so I must round this to 0.67, 2 significant digits. My answer can only be as significant as the least significant number used in the calculation. And that makes sense, doesn't it? Because I come over here in the universe and I make a really good measurement. You and I are lab partners. We're very, very careful. And over here we make a measurement and you and I are really sloppy because we don't care. Had a big lunch. Ugh. And we take those 2 measurements and we use them in some calculation. Our bad measurement screws it up, doesn't it? It doesn't really matter how good the measurement from over there is. This bad measurement gets in there and cocks up the works. Calculation is only as significant as the least significant number in the calculation. When it comes to multiplication and division, I'll give you an example. Pardon me. Oh, I have another example right here on this slide. Here I'm going to take 2.5 and multiply by 3.2. Again, two significant digits each, but when I put it in the calculator, I get 8. It somehow got worse. One significant digit, my calculator says. I need to realize that if I take two significant digits and two significant digits, I do that division, I need to know. I get 2 digits out of that. Scientifically, I report this as 8.0, 2 significant digits. Scheidly, you need to get a better calculator. No. My calculator doesn't know anything about significant digits. It can't know. Now, somebody's got a fancy calculator. No, Scheidly, I can put into scientific mode and set up tables and do this whole thing and it works. And yeah. Some folks have realized this. I can just keep it in my head and know what I'm doing and realize that I have a rule for significant figures. Well, the rules. I said that there would be a list of rules, and here they are. I don't even want to say it out loud. I don't even want to, dignify it. I'm gonna. All non-zero digits are significant. Right? Anything that's not a zero, that counts as a significant digit. Leading zeros are not significant because leading zeros, they just tell me the bigness or smallness of the number. Well, most often the smallness of the number. So leading zeros don't matter. Zeros between other zeros matter because when I write the number in scientific notation, I can't just get rid of those zeros. They're meaningful. Ending zeros after the decimal point are significant because that's the precision of the measurement. If you show me a 0 in the tenths place is the last number, then I know that that thing measures to the tenths, and that 0 means right on the money. 0th tick mark on that measuring device. So I could carry these around as a list or something, but I'd much rather think about it in the context of understanding that I'm working with numbers that are measurements, and what does the measurement mean? It's the meaning of things that is so much more valuable to me. So I realized something about multiplying and dividing, and I've just sort of written it here to be formal about it. That the result, when I multiply or divide, the result has as many significant digits as the number used in the calculation with the fewest significant digits. That's a formal way of saying that, but really what I mean is, chain is as strong as its weakest link. A calculation is as strong as its weakest number. Unfortunately, I got another example here. Pardon me. Got another example for you. If I take 11.3, that's 3 significant digits, and I multiply by 6.8, I have a number with 3 significant digits. That's 11.3. Doing it right now on my calculator. 11.3. 3 significant digits, and I'm going to multiply that by 6.8, which has 2 significant digits, and the result is 76.84. My calculator has no idea that I'm doing science. So 76.84. So I round that to 77 centimeters. I round that to 77 centimeters to be the result of the calculator. I wish that were the end of the story, but unfortunately, the rule is different when you're adding and subtracting. A little challenging to carry around 2 rules, but I'm sorry, you're going to have to. When I add or subtract numbers, the issue is not significant figures. The issue is precision. When I add or subtract, my answer is only as precise as the least precise number in the calculation. Here, I have 41.72. Now, 41.72 has 4 significant figures, but that's not relevant. What matters to me is that it has hundredths place in its decimal precision. I'm going to add to that 4.2. Again, doing it right here on my calculator as we go. I add to that 4.2. My calculator says 45.92. But this second number, 4.2, is precise to tenths. And so my answer can only be to tenths place. So I report it as 45.9. When I add or subtract numbers, it turns out multiplying numbers with significant figures is much more common than adding or subtracting numbers with precision. Chances are, if you're adding or subtracting numbers that are a result of measurement, they were made with the same measuring device. So they're going to have the same precision anyway. So it's rarely an issue. But for the sake of completeness, here it is, reported. Why does it matter? Dear golly. I was waiting for honors physics. I thought it was going to be so cool, and then it's significant digits and decimal places and whatnot. Who cares? Oh, it matters so greatly. It matters so greatly. Because as I said at the beginning, every measurement that I make with a measuring device. And every measuring device has a precision. The natural consequence of that is that every measurement made by mankind is uncertain. Now, that causes me a problem because at some point, I'm going to draw conclusions from those measurements. I'm going to look at those measurements and the calculations that I do, and I'm going to declare that I've discovered a physical law or a generalizing principle of the universe, that nature organizes itself in such a way, according to the observations that I've made. But if they're imprecise and if they're uncertain, I have to be careful about the conclusions that I draw from the data that I observe, from the universe that I seek to describe. So for example, here I have this 2x4. It's a little bit funny because a 2x4 isn't 2x4, is it? It's 1.5 by 3.5. At some point, some clever lumber mill salesman realized you could build a building perfectly well with boards that were a half an inch smaller on either side, charge the same amount of money for the board, make a fortune. So a 2x4 isn't actually 2x4. So I set down to measure it here with this ruler, and I'll defy the 2x4 inches and go for my scientific meters. And I measure it out with a centimeter ruler that has tenths of a centimeter on it, that is millimeters, tick marks. And I look at that edge all the way down the end, and I find that right around that spot where I declare what that measurement is, there is uncertainty. And it is that uncertainty in measurement that I am interested in managing so that I can draw true and appropriate conclusions from my observations, my description of